This video looks at the equilibrium of rigid bodies for Unit 6 of the WJEC Further Mathematics specification. Specification says that we should be able to understand and use the equilibrium of a single rigid body under the action of coplanar forces where the forces are not all parallel. Now it's important that we can calculate the moment of a force about a point. We need to realise that the unit for moment is the Newton metre, and that strictly speaking the moment of a force is a vector quantity if, with the direction of the moment being at right angles to both of the force and the line joining O to the force. So that is out of the plane containing the force and O. If the force is giving us an anti-clockwise turning effect, then we have got a positive moment. But if the force is giving a clockwise turning effect about O, then we have got a negative moment. The resultant moment of a system of forces is found by simply adding the moment of each of the forces. If a body is in equilibrium, there must be no turning effect, so there must be no resultant moment or zero resultant moment. And in most examples we will express this as saying that the total anti-clockwise moment must equal the total clockwise moment about a point. Now it's worth just looking at this quantity FD sine alpha in two different ways. We can, to begin with, say that FD sine alpha is the magnitude of the force multiplied by the perpendicular distance of O from the line of action of the force. Alternatively, we could say that the moment of the force is F sine alpha times by d, which is the component of the force perpendicular to the line OP, times by the distance OP. And you may find either of these two formulations of the moment of a force useful. If we've got a rigid body which is in equilibrium, then the resultant force acting on the body must be zero, and the resultant moment of these forces about any point must be zero. And when we're tackling rigid body questions, once we've drawn a good clear force diagram, we can proceed by either resolving in two directions and taking moments about a single point, or resolving in one direction and taking moments about 2 points, or by taking moments about 3 points that do not lie in a straight line. In practice, I usually use the first of these three options, in other words, resolve the forces in two directions and take moments about just 1 point. We've also got to remember the rules linking the frictional force at a point to the normal reaction at the point. In other words, that F, the frictional force, is less than or equal to mu times the normal reaction in general. But if the equilibrium is limiting equilibrium, then we've got the frictional force is equal to mu times the normal reaction. So, looking at our first example, which comes from the 2015 paper, we have a uniform ladder of mass 20 kilograms and length 6 meters, with its top end against a smooth vertical wall, its bottom end on rough horizontal ground. The ladder is inclined at an angle theta to the horizontal. The coefficient of friction between the ladder and the ground is 0.6. A man of mass 80 kilograms climbs the ladder. When he reaches 5/6 of the way up the ladder is in limiting equilibrium, and we have to calculate the normal reaction at the wall and the value of theta. And finally, we have to state a modelling assumption. So we start by drawing a good, clear force diagram. So there's the ladder, and the ladder has got a mass of 20 kilograms, so it's got a weight of 20 g, acting at its midpoint. The man is 5/6 of the way up the ladder, so there's a force of 80 g acting down on the ladder 5 meters up the ladder. The ladder is resting against smooth wall, so there is simply a normal reaction at the wall, but it's resting on rough horizontal ground, so at the base of the ladder there's going to be a normal reaction and a frictional force. So if we now start thinking about obtaining the equations from the equilibrium of the ladder, if we start by resolving vertically upwards, we have R2 minus 20g minus 80g must equal 0. So we've got R2 must equal 100g or 980 newtons. If we resolve horizontally, we have R1 minus F must equal 0. So R1 must equal F. But we know that the equilibrium is limiting, so F must equal mu times R2, which is 0.6 times 980, or 588 newtons. So we've got R1 is 588 newtons. So, just updating my diagram, I've got R1's 588 newtons, I've got R2's 980 newtons, and I've got the frictional force is 588 newtons. Okay, we've obtained those by considering the resultant force. We haven't yet, though, considered what's happening with the moments. So we're going to take moments about the bottom of the ladder. So about the bottom of the ladder, we've got the clockwise moments. So the total clockwise moments have got to equal the total anti-clockwise moments. The force R1 is going to be the only force that is trying to turn the ladder clockwise. So we've got 588 times by the perpendicular distance between the line of action of the force R1 and the foot of the ladder. And that perpendicular distance is exactly the height of the top of the ladder from the base, from the ground, which is the length of the ladder times by sine theta, so it's 6 sine theta. So I've got 588 times by 6 sine theta is the total clockwise moment about the base of the ladder. And that's got to equal, first of all, the moment of the 80g about the base of the ladder plus the moment of the 20g about the base of the ladder. The line of action of the 80g is at a distance of 5 cos theta from the foot of the ladder, because we know the man is 5/6 of the way up the ladder. In other words, the man is 5 meters up the ladder. So the moment of the 80g about the foot of the ladder is 80g times by 5 cos theta. The moment of the 20g is given by 20g times by the perpendicular distance of the line of action of the 20g from the foot of the ladder. The 20g is acting at the midpoint of the ladder, which is 3 meters up the ladder. So the perpendicular distance that we've got of the line of action of the 20g from the foot of the ladder is 3 cos theta. So tidying that up now, we've got 3,528 sine theta is equal to 4,508 cos theta. So we've got tan theta is 4,508 divided by 3,528. So theta is just under 52 degrees. Throughout the question, we've been assuming that the ladder is basically a uniform thin rod, rather than it being two parallel rods linked with a whole series of rungs. Moving on to our second example, which comes from the 2016 paper. We have a uniform rod AB, which is in limiting equilibrium with its end A on rough horizontal ground and the point C resting against a smooth fixed peg. The rod is inclined at an angle of 60 degrees to the ground. We've got the distance AC is x meters. The coefficient of friction between the rod and the ground is 0.3. We have to start by drawing a diagram showing all the forces acting on the rod and making it clear where these forces are acting. Okay, so the first thing is we've got the rod has a mass of 25 kilograms, so its weight is 25g, and that acts at the midpoint M of the rod. We're then, at A, going to have the contact forces between the rod and the ground, and that will consist of a normal reaction R together with a frictional force which is opposing the slipping of the rod. And there will then be a normal reaction at C, since the peg C is smooth, there will be no frictional force at C. So we've got our normal reaction, which we've labelled R1, acting at C. So there's our force diagram. Okay, now moving on to our second page here, we've got the force diagram again, and the only thing that we've added to that force diagram is a horizontal line at C. We know that the angle between the horizontal line and the rod is 60 degrees. The angle between the rod and the normal reaction is 90 degrees. So therefore the angle between the normal reaction and the horizontal is going to be 30 degrees. So we can now start by resolving the forces vertically. If we resolve vertically, we have the vertical component of R1, which is R1 sine 30, plus R minus 25g must equal 0. and that simplifies to 0.5 R1 plus R equals 245. If we resolve horizontally, we've got R1 cos 30 minus F must equal 0. But we know that we have equilibrium, limiting equilibrium in this case, so F is 0.3 R. So the equation that we've just written down from resolving horizontally can be rewritten as 0.866 times R1, take away 0.3 R is equal to 0. So we've got a pair of simultaneous equations linking R1 and R, which give us R1 is 72.3 newtons and R is 208.8 newtons. So that leaves us having to find the value of X. And to do this, we're going to take moments. Since both R and F act through the point A, neither of those will have a moment about the point A. So the easiest place to take the moments about is about the point A. And we can say that the clockwise moments have got to equal the anti-clockwise moments about A. The clockwise moment is produced by R1, which is trying to turn the rod clockwise about A. And the clockwise moment is going to be R1 times by X, because R1 is acting entirely perpendicularly to the rod AB. So we've got R1 times X must equal the anti-clockwise moment, which is given by the 25G. We need the distance of the perpendicular distance of the line of action of the 25G from A. So that line of action of the 25G is the vertical line. We know that A to M is 5 meters long, so the distance between A and the line of action of the 25G is going to be 5 cos 60, or 2.5 meters. So we've got R1 times X must equal 25G times by 5 cos 60, which gives me X equals 8.47 meters. Now for our next example from the 2011 paper, we have a uniform plank AC of mass 15 kilograms and length 1.2 meters, hinged to a vertical wall at A. The plank is supported in a horizontal position by a light rigid rod BD, where D is on the wall and B is the midpoint of AC. The length of AD is 0.8 meters, and a boy leans on the plank at C, exerting a force of 20 newtons vertically downwards. So we have to find the thrust in the rod BD, and we also have to calculate the magnitude and direction of the reaction at the hinge. We'll start by putting the measurements that we know onto the diagram. And now we will add the forces that are acting on the plank AC. We have the weight of the plank, which is 15G. We have the force exerted by the boy on the end of the plank of 20 newtons. We have the thrust, or the supporting force, provided by the rod BD. and then we have the reaction force at A. Now the reaction force is an unknown force acting in an unknown direction. Rather than dealing with a force of an unknown magnitude and an unknown direction, it's actually neater to suppose that this reaction force has got a vertical component and a horizontal component. Now it's very easy to see from the diagram that the horizontal component must act to the left. On the other hand, it's not at all immediate which direction the vertical component will act in. So we'll put it acting vertically upwards. If we're wrong about this, all that will happen is that the value of y will turn out to be a negative value. And if the value of y turns out to be a negative value, it means that I have got, instead of an upward vertical component, I've got a downward negative component. Okay. Just a little bit of trigonometry to do. The fact that we've got AD is 0.8 and AB is 0.6 tells me that tan theta is 0.6 divided by 0.8, which is 3/4. It also tells me that BD is the square root of 0.6 squared plus 0.8 squared, so BD is 1 meter. So we know that sine theta is 0.6 and cos theta is 0.8. So we can now start trying to find the thrust in the rod BD. So if we start by resolving vertically, then we have got y plus the vertical component of t, and the vertical component of t is t times cos theta, minus the 15g minus the 20 must equal 0. So we've got, when we simplify that down, y plus 0.8t must equal 167. If we consider the forces, or the components of the forces in the horizontal direction, then we have the horizontal component of t, which is t sine theta, minus x must equal 0. In other words, we've got 0.6t, take away x, equals 0. We're now going to need to take moments. And we're going to take moments about B. And the reason for taking moments about B is simply if we take moments about B, the awkward force, T, has no moment about B. The 15g has no moment about B. X has no moment about B. So all we've got to worry about is the moments provided by the y and the 20. Now both the y and the 20 are trying to turn the plank clockwise about B, and the moment of them is y times 0.6 plus 20 times 0.6 is the total clockwise moment, and that must equal 0. Of course, we've got to have total clockwise moment equals total anticlockwise moment, and there is no anticlockwise moment. And if we simplify that equation, we end up with y equals minus 20. So that does indeed tell me that I have got y acting in the wrong direction on my diagram. So, in fact, the vertical component of the reaction at A is 20 newtons acting downwards. Okay, now I know that y plus 0.8t has got to equal 167. So that's minus 20 plus 0.8t equals 167. So t must be 233.75 newtons. We know that 0.6t minus x equals 0. So we've got x is equal to 0.6t, which is 140.25 newtons. So the reaction at A can be regarded as being the resultant of a downward vertical force of 20 newtons and a horizontal force of 140.25 newtons acting to the left. Pythagoras' theorem will give us that the magnitude of this reaction is 141.7 newtons, and we have tan alpha is 140.25 divided by 20, so alpha is the inverse tan of 140.25 divided by 20, in other words 81.9 degrees. So the reaction force is 141.7 newtons at an angle of 81.9 degrees to the downward vertical. For our final example, we have a uniform triangular lamina of weight 1890 newtons. Triangle is isosceles with AB equals AC. The midpoint of BC is the point M, and we're told that A to M is 3 meters. We have angle MAB is beta, where tan beta is less than 5/12. The lamina is held in limiting equilibrium in a vertical plane by a light cable attached to M, with the vertex A on rough horizontal ground and AM making an angle alpha with the ground, where tan alpha is equal to 5/12. The cable makes an angle of theta with the horizontal, and the coefficient of friction between A and the ground is 0.75. And we have to find the normal reaction between A and the ground, and the tension in the cable, and the value of the angle theta. So, we need to start by drawing a good force diagram. Now, if we're going to draw a good force diagram, we know that the weight of the lamina is 1890 newtons, but we need to determine the centre of mass. Now, for a triangular lamina, the centre of mass is 2/3 of the way along any median, and the median is the line that joins a corner of the lamina to the midpoint of the opposite side. Now we're told that A to M is 3 meters, so the centre of mass of the triangular lamina is going to lie 2 meters from A and 1 meter from M on the line AM. So there's the centre of mass, and we have the weight of 1890 newtons acting through that centre of mass. We have the tension in the cable there, and then we have the normal reaction and the frictional force acting at A. So, to proceed, we'll resolve vertically and horizontally and then take moments. So, resolving vertically, we have t sine theta is the vertical component of t, plus r minus 1890 must equal 0. So we've got t sine theta plus r must equal 1890. Resolving horizontally, we have t cos theta minus f must equal 0. So t cos theta must equal f. We know that the lamina is in limiting equilibrium, so we've got f must equal 3/4 r. Now we've now got 3 equations, but we've got 4 unknowns. We've got t, we've got r, we've got f, and we've got theta. If we're going to make any progress, we're going to need to do something else, get another equation, and that's going to have to come from taking moments. Probably the easiest place to take moments about is m. So taking moments about the point m, because that's going to eliminate both t and theta, then we can say that the clockwise moments have got to equal the anti-clockwise moments. The forces r and f are going to be trying to turn the lamina clockwise, while the force of 1890 newtons, that's the weight of the lamina, is going to be trying to turn the lamina anti-clockwise. The perpendicular distance of m away from the line of action of r is going to be 3 cos alpha. So the moment of r about m is going to be r times 3 cos alpha. The perpendicular distance of the line of action of f from m is going to be 3 sine alpha. So we've got the moment of f about m is f times 3 sine alpha in the clockwise direction. We know that the centre of mass is just 1 meter away from m. So the perpendicular distance of the line of action of the 1890 newtons from m is just going to be 1 times cos alpha, in other words cos alpha. So the anti-clockwise moment that we've got is 1890 times by 1 cos alpha, in other words 1890 cos alpha. Now if we take that equation and make use of the earlier equations, we are going to make a lot of progress. So there are the 4 equations that we've set up. We've got the fact that tan alpha is 5/12. If tan alpha is 5/12, then the hypotenuse on that triangle is of length 13. So we've got sine alpha is 5/13, cos alpha is 12/13. So the moments equation can be simplified quite a lot. It can be simplified to r times 3 times 12/13 plus 3/4 r times 3 times 5/13 equals 1890 times 12/13. Tidy that up, we've got 189 over 52r equals 22,680 over 13, which simplifies to r equals 480 newtons. Now I know that r is 480 newtons, then I've now got t sine theta plus r must equal 1890, which tells me that t sine theta must be 1,410 newtons. And we've got t cos theta is going to be equal to F, which is 3/4 R, which is 360 newtons. So I now know that T has got a horizontal component of 360 newtons and a vertical component of 1410 newtons. So the magnitude of T by Pythagoras is 1455 newtons. And we have got that theta is tan to the minus 1 of 1410 divided by 360, so that is 75.7 degrees.